All right, everybody, get ready, because we are diving into some seriously mind-bending stuff today, even for us. We're talking quantum mechanics, but with a twist. We're looking at this research paper, and get a load of this title: Quantum Mechanics Without Quanta.
Yeah.
Like, seriously, that's what it's called.
Bold.
And it's even wilder than it sounds.
Yeah.
They're saying we might not need all those crazy concepts like photons and particles to make sense of quantum stuff. What if, and I'm just throwing this out there, what if all this quantum weirdness is actually rooted in plain old classical physics? Luckily, we've got our expert here to guide us through this. They're kind of the best at explaining this stuff without making our heads explode.
I'll do my best.
So light, right, everyone's heard about this whole wave-particle duality thing.
Right.
Sometimes light acts like a wave, sometimes a particle, and everybody's supposed to just accept that.
Yeah, it's definitely one of the weirder parts.
It's more than weird. It's like fundamentally confusing.
Yeah.
So this paper I mentioned, they're like, hold my beer. What if there are no photons?
Okay.
Like, at all.
Interesting.
What if light is just a wave, it's good old-fashioned wave, and all those quantum effects we see are just because of how that wave interacts with matter? You know, those tiny, chunky atoms.
You know, that's actually not a totally new idea. Planck and Schrödinger, those guys way back when, they kind of messed around with similar thoughts.
Really?
Yeah. What's cool about this paper is they're pointing to some semi-classical explanations for things we usually use to prove photons exist.
Wait, like what?
Like the photoelectric effect, the Compton effect.
Hold on. Those are like textbook examples of why we think photons are real. Are they saying we got it all wrong?
Well, maybe not totally wrong, but maybe we've been misinterpreting the evidence.
Okay, now I'm really interested. But if light's not this weird hybrid thing, what about all the rules? Like, what about the Born rule, the one that connects light intensity to the probability of finding a photon?
So that's where things get really wild. This paper is suggesting the Born rule might actually just emerge naturally from this new perspective.
Okay.
It's not really a fundamental law, but more like a consequence of good old wave mechanics and the fact that matter is made up of those discrete, chunky atoms.
So instead of like ripping up the rule book of physics, we're just reading it from a different angle.
Something like that, yeah. Maybe we're not rewriting the laws, just our understanding of what those laws are describing.
This is seriously messing with my brain here. Okay, so light, maybe not so weird after all.
Maybe.
But hold on tight, because this paper, they don't stop there. Now they're coming for the electron.
Oh, boy,
Electrons, right. Those tiny little guys zipping around atoms. We've all seen the diagrams.
Yeah.
But they also act like waves sometimes. Classic quantum weirdness, or so we thought.
Right.
But get this paper asks, what if, and there's a big one, what if we just ditch the whole particle idea for electrons entirely?
Okay, now you've got my attention.
What if the electron isn't a tiny ball of charge at all, but more like an electron wave?
An electron wave.
Like a continuous field, kind of like light, but with its own unique properties.
I'm trying to picture that.
Okay, I know. Hold your horses. An electron wave. How can you have charge spread out like that? We're used to thinking of it as this tiny little speck.
It's definitely a shift.
What would an electron wave even look like? Help us out here.
So, it is pretty out there, but it's fascinating. What they're saying is all those quantum equations we use, like the Dirac and Schrödinger equations, those would actually be describing this electron field, not just the probability of finding a particle.
So instead of tracking a tiny billiard ball, we're mapping out a whole, wave.
Exactly.
But electrons have charge, they have spin, a magnetic moment, all that stuff. What happens to those properties in this wave picture?
That's the really cool part. They show how this electron wave, even though it's spread out, it would still have a kind of angular momentum, a magnetic moment.
Wait, really?
Yeah.
How do you even...
It's kind of like, imagine a smoke ring, right? It's got that spin, even though it's not a solid thing.
Oh.
It's like that.
So you're saying those fundamental properties, like charge, spin, they're not something the electron has, but something it is. Like, they're built into the very fabric of this electron wave.
Exactly. It kind of changes how we think about those properties, what they even mean. And remember that double-slit experiment we were talking about?
With the light?
Yeah. They're saying this electron wave interacting with the detector, that could be what explains the results we see there, too, just like with the light.
So both light and electrons, more like waves washing over this, bumpy landscape of atoms rather than tiny little bullets.
It's a different way of looking at it, that's for sure.
I'm starting to get it, but this has to have some pretty big implications, right? Like, what about all the rules we thought were governing this quantum world? the Born rule, all that stuff.
So they actually address that too. They say the Born rule, that thing about the wave function and the probability of finding a particle, it actually emerges naturally for electrons too in this framework. At least under certain conditions.
So it still works.
Yeah, it's just, it might not be a fundamental law like we thought. It could be more of a consequence of this continuous wave interacting with those discrete little chunks of matter.
Okay, so we're not throwing out the rule book entirely, just like reinterpreting it.
Exactly. It's a new lens to look at the same phenomena.
So it's not the light or the electrons themselves that are so freaky-deaky quantum. It's how those continuous fields interact with, the stuff of the universe, those chunky atoms.
Really flips the script, doesn't it?
Totally. But even with this whole electron wave thing, we still got some big, quantum-sized questions, right?
Like what?
Like, what about the Heisenberg uncertainty principle? The big one. If there are no actual particles, how can you say we can't know both the position and momentum of an electron at the same time?
See, that's what I love about this whole new way of looking at things. It gives us a fresh perspective on even the weirdest parts of quantum mechanics. Like, the paper suggests that maybe the uncertainty principle isn't about limitations in how we measure things.
You're saying it's not our fault?
Not necessarily, no. It could be a fundamental property of the waves themselves.
You mean like the electron waves?
All waves. Think about it like a sound wave, right? Can you tell me exactly where it is and know its wavelength perfectly at the same time?
I mean, I don't think so.
Exactly. It's like trying to, nail down a ripple on a pond. The more you try to define its position, the less you can know about its motion.
So it's not that our instruments are messing things up, or that we're just bad at measuring.
It's baked into the very nature of waves. And since we're picturing electrons as waves now, the uncertainty principle just kind of falls into place.
Okay, I think I'm actually starting to wrap my head around this, but there's one last thing I got to ask about. The Compton effect.
Ah, yes. The granddaddy of them all.
That's where light acts like it's knocking electrons around, like billiard balls or something. Isn't that the classic example of light acting like a particle? Can this paper really explain that without photons?
It can certainly try, and it does a pretty good job, actually. Remember, no particles in this framework, only waves.
Right, right.
So instead of picturing a photon smacking into an electron, try to imagine the electromagnetic wave, which is light, scattering off the charge distribution of the electron wave.
So it's more like an obstacle course. The electron wave, with its spread-out charge, is like a bunch of obstacles for the light wave to navigate.
Exactly. And that interaction, that's what produces the results we see in the Compton effect, but without any actual particle collisions.
Pretty neat, huh? Okay, that's seriously mind-blowing. This whole deep dive, it's like we took a trip down the rabbit hole and ended up questioning the very fabric of the universe. No photons, no particles, just waves, fields, all interacting in ways that, honestly, I'm still trying to wrap my head around.
It's a lot to take in.
It really is. A huge thank you to you for, walking us through all this crazy stuff. I think we both need to lie down after that one.
You said it.
And to all of you listening, thanks for coming along for the ride. It's really got us thinking, if we can understand quantum mechanics like this as this classical field theory, does that change how we see the universe? Does it make it less weird or just way more mysterious? We'd love to hear your thoughts. Until next time, keep those what-if questions coming, and happy diving, everybody.